So when I asked the question, I thought that the answer would be blockchain, and I guess you guys agree. It would be blockchain, it would be stablecoins, and it would be Forex on blockchain. And that's what our project, Pendulum, is going to address. So hello everyone, I want to welcome you to this presentation about Forex markets on blockchain. I'm actually CTO of Pendulum. I'm Thorsten. I have a PhD in computer science, theoretical computer science actually. That's a long time ago. I've been working in the blockchain field already for 5 years. And before that I was a founder for web development companies in different fields. I feel like there's a little bit of feedback here. Yeah. So before we talk about the more technical topics, I want to give a little bit of context what Pendulum is about so that it makes more sense why these topics are important for us. First, Pendulum is a parachain project. And when you talk about parachains in the .sama ecosystem, of course, you always talk about usually two different ones. The main one, of course, is Pendulum, which is on Polkadot. Not yet, but it will be very soon because we are going to join the auction in 2 weeks. And then the goal would, of course, be that it goes live in February. Very exciting times for us. But we're actually already live on Kusama, and our Kusama equivalent chain is called Amplitude. And as all you guys know, parachains are not general blockchains, general purpose blockchains, but they're special purpose blockchains. And so also Pendulum is a special purpose blockchain. And our mission is to connect the fiat networks with the DeFi ecosystem. What that actually means is that we want to become the central hub for all DeFi applications for stablecoins and fiat tokens on Polkadot. And to be more specific, we are tailored for Forex. That means that, of course, the Forex market is a very important use case for us, and we want to tackle the problems that I showed in that little story I shared at the beginning. In addition to this, also other specialties for Pendulum would be that we integrate with local banks and fintechs. And what that actually means, I want to show in this example. This is an example of a cross-border payment, also a very important use case for Pendulum. It's a cross-border payment, in this example, from Europe to Tanzania. I'm in Europe, and I want to send euros to a recipient in Tanzania. And of course, I want to ensure that the recipient receives Tanzanian shilling in Tanzania, where Tanzanian shilling is the native currency in Tanzania, if you're not familiar with that. And in this example, you would use the local fintechs and banking integrations of Pendulum to tokenize a token in Europe into a euro token, and at the end of the transfer, you would detokenize a Tanzanian shilling token into Tanzanian shillings. But of course, in that whole cross-border payment, one component is missing, and this is to actually exchange those tokens, namely euro token into a Tanzanian shilling token. And that's how the Forex AMM ecosystem on Pendulum comes into place. What I mean is an ecosystem of Forex optimized automated market makers, or dapps. And in this case, Forex optimization means that they're Forex optimized price curves, because Forex is only for stablecoins, for fiat-backed tokens, and they have different properties than your average crypto token, which is much more volatile, for example. So you can optimize the price curves for this. Also, you have, for example, single-sided liquidity pools, which is also an optimization, or you have a backstop pool, for example, in USDC, and this lowers the risks for the liquidity providers. And of course, I will talk more about this in this presentation, where I go into the more technical topics. Now, when I talked about becoming a stable hub for stablecoins, just having fintechs and off-ramps and on-ramps is not enough. But another really important component is to actually connect to other blockchains that have a great supply of stablecoins, for example, Stellar or Celo. And what we came up with is a concept that we call Spacewalk, which is a bridge concept for Polkadot optimized for stablecoins. And I say Polkadot, although Spacewalk is a bridge to Pendulum, it also makes all those tokens and stablecoins from other ecosystems available for all of Polkadot. As you know, there are all these built-in bridges in Polkadot through XCM. But since this is starter space, I will keep everything a little bit more basic and don't assume that you have already any kind of knowledge about how Polkadot works. But inside of Polkadot, you have this nice relay chain that connects all the parachains to each other and allows free token transfer. Now, just as the final summary about our project, important components that I just mentioned are the local fintech integrations, then the Spacewalk bridge to bring in tokens, and finally, an ecosystem of Forex AMMs. And I want to use this as an agenda for this presentation to go deeper into the technological side of the Spacewalk bridge and of our Forex AMM, or of how AMMs work. Okay, let me start with Spacewalk. If you have any questions, feel free to interrupt me. We have enough time here, so yeah, you can hand down the mic. But yeah, let me start with Spacewalk. I already said that Spacewalk is first and foremost a concept, a unified concept for bridging stablecoins in Polkadot. But from a more technical standpoint, that means that it is a bridge standard for .sama, or even more technical, it's just bridge standard for substrate-based chains. Can also be standalone chains, doesn't matter. What that boils down to is that Spacewalk is a pallet, or it's actually a group of pallets that you can plug into a parachain, and then you can enjoy the power of Spacewalk also in your parachain. It's not just limited for Pendulum. Of course, we are going to use Spacewalk in Pendulum, but it's totally independent. It's its own repository. It's really written independently of Pendulum so that it's available for all parachains. If you want to use it in a parachain, as I said, it boils down to a group of pallets and also some services that you need to run in addition to this, because there's probably some oracles that you need to run, some off-chain logic for custodians, and so on. It really depends on what kind of ecosystem you want to bridge to. I also want to point out that Spacewalk has been supported by a Web3 Foundation grant, and that's also one of the reasons why we made it as an ecosystem project and not a project integrated in Pendulum, but as an independent project that can benefit all parachain projects, for example. When we designed Spacewalk, we had also 3 criteria in mind that are really important for us. And the first one would be that it's truly decentralized. Everyone probably became familiar this year with all the unfortunate attacks on bridges. And there was just recently, I think like 3 weeks ago, there was an attack on the Binance bridge where someone stole, I don't know, was it 100 million or 600 million, somewhere in between, but it was a lot of money. When this year started, I think in March, there was also a big attack on another bridge where someone also stole $600 million, and I will go into more details why this happened in the first place. But quite often it boils down to either that there are bugs in the bridge, or, which is maybe a more fundamental problem, namely that the bridges are not truly decentralized. Either they are totally centralized from the beginning, just like the first generation of bridges, they were quite centralized, but still a lot of bridges are not decentralized enough for our standard of decentralization. For Spacewalk, that's different. Spacewalk is truly decentralized, and I will show an example later that makes clear that it's not just halfway in between decentralization and centralization. Furthermore, Spacewalk is also trust minimized. Depending on the blockchain that you want to bridge to, and I will show an example later, it could always happen that you need to interact with human actors, with custodians, for example, if you want to bridge tokens. And in Spacewalk, these human actors are economically incentivized not to misbehave and to, for example, run away with tokens. If they do anyway, then you're guaranteed to get your money back. And I will also show an example why that happens. Thirdly, Spacewalk is censorship resistant. That means that, again, if you have to interact with a human actor, it could always be that that human actor denies service to you. Human actors are always free to do this. It's not smart contracts. But since it's a decentralized network, you can always go to another human actor or another agent, or you can also become your own agent in the decentralized network, and by that, Spacewalk will guarantee service to you at the end. I said that Spacewalk is a unified concept, or to build a bridge or stablecoin bridges for Polkadot, and I also said that it's meant to integrate in different ecosystems. And so what you do is that there are pluggable components in that abstraction layer that's at the bottom, and the pluggable components then take care of different logics that apply to different ecosystems. Now, after this more theoretical consideration, I want to jump into a concrete example, and this would be the bridge to Stellar. I particularly mention this example here because first, Stellar is very important for our use case, as Stellar is a supplier of great stablecoins. I don't know whether you're familiar with Stellar. Stellar is, or used to be, a very well-known blockchain, but they don't have smart contracts yet. And maybe for that reason, they fell a little bit into the background, are not one of the most well-known blockchains anymore. But they did one really great thing, namely they have a lot of integrations in different countries with fintechs and banks in order to on-ramp fiat coins and tokenize them. And they so far have 15 of these fiat coins, for example, in Nigeria, Tanzania, I already mentioned that, US of course, but also Brazil, another set of third world countries, Canada, Australia, and so on. And that's really important for cross-border payments or for the Forex market. And of course, we want to tap into this rich ecosystem of stablecoins, and that's why there is a Spacewalk Stellar instance. I also want to talk about Stellar because Stellar is particularly complicated to bridge to. And in order to understand why that's the case, I think we need to look at typical bridges that you find. For example, let's look at a bridge into a proof-of-work chain. Ethereum is not proof of work anymore, so that does not apply to Ethereum in that way anymore, but for a long time it was definitely the typical way how bridges worked to the big blockchains. And this is that chains that are based on proof of work, they have certain capabilities and certain properties that you take advantage of in order to bridge or to make the bridge reliable. And first of all, you have Nakamoto consensus, and that means that if you know all the headers of all the blocks that exist in the blockchain that have been created so far, then you can just look at the header, and every header contains a link to the previous header because there is a hash of the previous header inside that header. And so you can take all the headers and you can arrange them, and you can order them, and then what you see is that these headers then create a list. Well, actually it's not a list, actually it's a tree, because there are also forks, but in general there will be one longest chain in that tree, or one chain with the highest weight, and that's usually considered to be that subchain that represents the current truth. It can always roll back, there can always be a change, but usually just in the recent history. Otherwise it would be way too hard to roll that truth back. So if you just know the headers, you also know what's the current status and what's the current truth and what's the current valid chain. Now, if you only know those headers, that's not enough information yet to know what actually goes on inside each block, because that's what you're actually interested in. You want to know what actually happened, what kind of transaction happened, for example, on Bitcoin or on Ethereum when it was still proof of work. But what you then do is that you take advantage about how the transactions are structured inside each block. The transactions in a block are usually not arranged just in a list, but they are in this tree structure, in the Merkle tree structure, and that makes it very efficient to prove that a certain transaction is really inside the block. So the only thing you need to do in order to show or to prove to an automated system that a certain transaction is inside the block, if that system only knows the header of the block, is that you identify the path from the position where the transaction is. There will be here in some of the leaf nodes. You traverse the path to the top, and then you provide only a proof about this path. You only show that there's a sequence of hashes when you go up that path, so that at the end you really arrive at the hash of the main hash, the Merkle root that is stored inside the header. And that's very efficient, because even if there are 1,000 nodes or 1,000 transactions in that block, you only need a proof that has only 10 hashes, because it's logarithmic. It scales logarithmically, and you want efficiency in the bridge. You don't want to always provide the complete set of blocks, of transactions on a block in order just to prove that a certain transaction is in there, because you want a scalable bridge. And for example, in the Ethereum ecosystem, where all of these computations need to happen in the EVM, that is already very slow. I mean, depending on the blockchain that you bridge to, the hashes that are computed there might not even exist as precompiled contracts, and you need to implement that logic directly inside a smart contract, and it's very slow. computing a hash function in a smart contract, because it's an exotic hash function, will be painfully slow, and for that reason, it's really good that you have these worker trees in the first place and could do it efficiently. Then another problem, Stellar, is also that you don't have smart contracts. I already mentioned that. And if you don't have smart contracts, you need to replace smart contracts that are reliable, that you can study in advance. You need to replace them with human actors, and they can misbehave. So, and all of that combined means that you don't have this classical chain relay that you might have, for example, for a bridge to Bitcoin or to Ethereum or to other blockchains. You need to come up with a new concept for Stellar. Before I talk about that concept, let's try to get a general understanding about how bridges works. And again, I assume that we are here in the starter space, so I might talk just about the basics here in case you're not familiar with bridges. So in a bridge, well, let me first start that the notions I take here are actually taken from the inter-BTC bridge, from the interlay parachain, because the Stellar instance of Spacewalk is actually built based on inter-BTC bridge. And the notions to be used is the issue, and issue means that someone wants to move a token from the source chain to the target chain. The source chain in this example, of course, is Stellar, and the target chain is Pendulum, or can be any other parachain that uses Spacewalk. Issue operation now means that you simulate a token transfer. And I say simulate because bridges cannot really move tokens from one chain to another chain. It's impossible. A token always can only stay inside a chain, but a bridge basically simulates a transport. And that works by first moving a token from the source chain into a certain account, which I call a locking account here. You put that token into that account, you lock it there, you render it unusable for a certain amount of time. And why it's unusable, basically disappears, so to say, when it's unusable. And why it's unusable, you can then mint a token, an equivalent token on the target chain and send it to some target account. So that at the end, it's a zero-sum game. The number of available tokens in the complete system still stays the same, but you just need to ensure that while this token exists, you don't unlock that token. And you also want to ensure why this token is locked, this token is still in existence and gets minted. So there always needs to be some synchronization between both chains, and that's actually the whole magic of the bridge, that the bridge needs to synchronize that. Now this is called the issue operation, because you mint the token on the target chain, and of course, eventually you want to move that token back, and that's what is called redeem in the world of interlay. You move that token back into the pallet. So this is actually meant to be the smart contract, but it's not a smart contract, it's actually a pallet, but the pallet is basically the equivalent of this. You move that token back, it gets burned, you don't want to have it anymore, and then you do the precisely the opposite on Stellar. You unlock the token and you send it back to the recipient. So that's the very simple basics of how every chain works, or every bridge works. Now, the main problem is still the locking account. When you have that locking account, or let me go back to the previous picture, it's a little bit cleaner. When you have that locking account, you need to ensure that the token doesn't get unlocked or is not used for any other purposes. Think of FTX, for example. So if this is not controlled by a smart contract, then it's controlled by a human actor. Human actor has the keys and could do whatever they want if they are the owner of this account. If it's a smart contract controlling the account, then everything is fine. You can study and analyze the smart contract and can ensure that the smart contract behaves exactly as you want it, and it definitely keeps the token reliably locked. But on Stellar, we don't have smart contracts, and that's why it will be controlled by a human actor. And now, a typical scheme that you apply in this situation is that you use a decentralized authority, or there are also other words for this. But what that means is you don't have a single human actor, but you have a group of human actors that control that account. Or this a committee of account owners, so to say. Or you also call it an N out of M multi-signature account, because N people out of this M, let's say you have N people that control the account, you say that N of them, which is a smaller number, they need to sign any transaction together, they need to mutually agree that a certain transaction is valid, and then you can still tolerate that maybe there are some foul apples in your group of co-signers. There could be a scammer in between, but you can tolerate that because you still expect that at least n are reliable. And that's maybe good enough, but let me just check something. But the problem is that this is not good enough for every bridge. And actually, I talked about this attack on a bridge in March or April this year, where a single hacker stole $600 million. And that was because we had precisely the situation with the decentralized authority. I think it was a bridge with a 5 out of 9 multi-signature account, which might sound safe, but a hacker was able to take over 5 of those accounts through, I don't know, social engineering or any other kind of actions. And so for that reason, this is not decentralized enough. And of course, you can try to improve that situation by introducing more co-signers, by maybe having 100 or even an unlimited number of co-signers to have some real decentralization. But the problem is that in the Stellar network, you only have a limitation of up to 20 co-signers for a single account. And I would still say that 20 co-signers is not really decentralized for every situation. So I think it should actually be more than that. Another problem is that if you have this kind of decentralized authority and you want to have real decentralization, that actually means that it should be permissionless. That means that you would like to have a dynamic system where constantly new co-signers can come in. Co-signers that don't want to be part of that network or don't want to support that anymore should be allowed to leave. So it should be highly dynamic. And you need to find your own protocol how to arrange all of that. How you can have new co-signers, how they can introduce themselves. And that's actually not easy because you need to have all the old co-signers agreeing that there's a new one and so on. So it always requires some kind of protocol or permission. And yeah, and I already talked about the problem that a single hacker could take over the co-signers. Cyber attacks are definitely possible. Someone can impersonate many different co-signers, but it's actually one single person control or one single entity controlling them, and then you run into troubles. So for this reason, decentralized authority is not enough for our standard of decentralization. Now, the idea that we adopted is actually taken from InterBDC. And InterBDC is, to say that again, it's a bridge to Bitcoin. And it has similar needs as the bridge to Stellar because Bitcoin also doesn't have smart contract. So again, you need to deal with human actors on the Bitcoin side. And InterBDC is based on peer-reviewed research. There's a lot of work and brainpower that went into this system, and they really figured out how you can have a decentralized and secure bridge if the target blockchain doesn't have smart contracts. And for that reason, we adopted that. Also, while we were working on our Web3 Foundation grant, we got that feedback to actually base it on InterBDC because that's a very well-respected concept, and here we are. So to go into the main ideas of InterBDC and how InterBDC solves that problem is that first you introduce a system of vaults. What that means is you don't have a single locking account anymore, but you replace that single locking account by a complete set of accounts, which you call vaults in that system. And this is a totally permissionless and decentralized network of vault. Everyone can introduce their own vault. You can just register a vault, and then you're also a vault operator. You can always leave the set of vaults. There's some protocol behind that, but it's definitely not as complicated as the co-signer situation with the decentralized authority. So it's a totally dynamic set, and it's totally decentralized. I think you can recognize it because also it's totally unlimited. It can be an arbitrary number of vaults. So what that means is that decentralization is not reached through having multi-signatures or multi-sig accounts, but by having a decentralized network of vaults. Now, what you also see is that there is a new icon here on this side, because every vault is, of course, still controlled by human actors. Now, I just draw one human actor here per vault, but it can, of course, be also multi-sig accounts themselves. That doesn't matter to us. The vaults control and arrange themselves and manage themselves, but there will be at least one human actor. And now, I think it's on the next slide. No, not yet. And now what you do, or what InterBDC introduces, is that there is a collateral that the vault operators, they need to leave a collateral with the pallet before they are allowed to actually lock any tokens in the vault. And that incentivizes them not to misbehave because it's an over-collateralized system. If they run away with the locked tokens, then the collateral will be slashed, and at the end, they definitely lose money. And when the collateral gets slashed, it's actually open to arbitrageurs to come in and redistribute the tokens to the end users that lock their tokens in the account. So the arbitrageurs, they still get some money because it's an over-collateralized system. They still get some money. There's always a difference. But the end user would definitely get their money back that they locked. And by that, it's a system where the end users ensure that there's no incentive for misbehavior. Now, what I also show here is a price oracle. You definitely need a price oracle to ensure that the collateral stays over-collateralized. And the reason is that the tokens that you use for collateral and the tokens that you use in the vaults are different. If there would be the same tokens, you don't need the bridge in the first place. But the tokens in the vaults are tokens that are stablecoins that are in Stellar, for example, a Brazilian Real token or whatever, or USDC. And the tokens that you use for the collateral would, for example, be dots, because they have a high security and they're available to every parachain, of course, through XCM. And then you constantly need to check whether the prices of DOT tokens and of the stablecoins that are locked in the vaults, whether there's still over-collateralization happening. If they get too close, like let's say 110% or 120% of each other, then it's time to actually liquidate the vault and give back the money to the end user in order to have everything in a safe way. Of course, vault operators can also observe that the prices get too close and they can always fill up the collateral in order to make sure that this doesn't happen in the first place. So now the final component, and that is the main component that's definitely very different from InterBTC, is what we call the Stellar Oracle. The Stellar Oracle is a component that transmits information from the Stellar side to, in this case, the Pendulum side. And this kind of information transport is incredibly crucial for every bridge. Basically, it's the weakest link in every bridge, and you need that in order to always make sure that what happens on the Stellar side is always reflected on the Pendulum side. For example, again, that if you want to issue a token, that means moving a token from the Stellar side to the target side, and you want to lock it in one of those vaults, then at the same time, the pallet needs to learn about this, reliably learn about this, and mint a token to send to the target. This needs to be obviously reliable, because if anyone can fake that information, if any hacker is able to fake that information and give spoofed information to the pallet, then the pallet would then just mint tokens and send to the target account, and then they can just immediately move back those tokens and would then steal money from the vaults. That's basically how a lot of bridge attacks work. Basically, it's always the same system. That's because this weak link, or the equivalent of this link in other bridge, that's where the hacker has the chance to get into and send wrong messages. And that's precisely also how the Binance bridge has been hacked 4 weeks ago or so, because of this component. Now, when we created the Stellar Oracle, we tried to make it as safe as possible. And this really taps into how Stellar works. And when I say as safe as possible, then our idea was that it is impossible to spoof information, and we want to have it as secure as the Stellar consensus protocol itself. And also I want to point out that maybe the word oracle is a little bit intimidating, because oracle, when you think of oracles, most oracles are somehow not fully decentralized, or there's always some possibility that someone feeds them with wrong information. The Stellar Oracle cannot be fed with wrong information, and I will tell you why this is actually the case when I go into a little bit more into the depth of the Stellar consensus protocol. Because this is the part where it really gets crucial how Stellar actually works. Now, Stellar is very different from actually basically all the other blockchains when it comes to how the consensus works. You're probably familiar with a lot of consensus protocols like proof of work, proof of stake, and so on. But in Stellar, they have a consensus protocol that is called Stellar Consensus Protocol. Who would have thought that? And Stellar Consensus Protocol is based on a consensus protocol called Paxos. I don't know, who's familiar with Paxos? Okay. So if you know a lot about consensus protocols, you know that Paxos was maybe mainly one of the first ones that solved a big problem in consensus theory. It was by Leslie Lamport, I think that's his name. Really great scientist. Also the one who's behind LaTeX, if you know LaTeX, and are from the science field. And he invented Paxos, but Paxos is actually super complicated to understand. There are now other consensus protocols that are a simplification of that one, like practical fault tolerance, which you have in Cosmos, for example. But still is based on Paxos in some sense. But they also use different methodologies that go further and go beyond. And what they have is that first they have a system of nodes, and every node expresses what other nodes it trusts in that system, in that network. So when you deploy a validator node in the Stellar network, you always pick other nodes that you trust, and you express that these are the nodes that you trust. And when you think of this mathematically, then, sorry? I will talk about this. If you think of this mathematically, then you have a graph. Yeah, so you express a network of trust, and this is why you do this. Is because this is how the Stellar Consensus Protocol is very much based on the system, and I will tell you why. Because, and that's actually what I displayed here as well. So when you in every consensus protocol, what does a consensus protocol actually do? You have different actors, different nodes in a decentralized network, and they want to agree on a common truth. And what they start with is that every node makes a proposal what they think the common truth should be. All these proposals are totally equal. None of them is wrong. But the whole goal of the consensus algorithm is that they need to decide on one single truth. And what you usually introduce is a system of quorums. A quorum is a subset of the network, and you need to ensure that the quorums always overlap. That's what I expressed here with those rings. And now what you want is that you wait until a single quorum decides on a common truth, and if that ever happens, you know that this common truth will then be adopted in the whole network. And the point is that quorums overlap. There will never be two different quorums that decide on different truths, because since they always overlap, there would be a single node that would decide on both truths, but the whole point of the consensus algorithm is that this cannot take place. A node will always decide just for one truth. And since you have this overlap, you can then make sure that there will be consensus at the end. And now this network of quorums, traditionally, it's very hard to do in a very dynamic way. Usually you have a predefined set of actors, you know who the actors are, and you define the set of quorums in a predefined way, and then you run your consensus algorithm. But that's very much is not how blockchains work. Blockchains are highly dynamic. You always want to allow new actors to come into the blockchain to start their validator nodes and to leave in a permissionless way. And for that reason, you need a very dynamic treatment of those quorums. And this dynamic treatment of quorums comes with this network of trust. So you have this network of trust, and in this network of trust, you will see that there is one subnetwork, which is if you look at this from a graph theoretical point of view, from a mathematical point of view, in case you're familiar with this, there will be it's a strongly connected component, and the maximum strongly connected component is a subnetwork that enjoys the highest level of trust and transitive trust. And this highest level of transitive trust is called the tier one validator network. And now what you observe if you study consensus algorithm is that you just need to look at the tier one validator network about what they decide. And what we do in the Stellar Oracle is that we intercept the messages that the nodes in that network send around when they do the consensus algorithm. Every consensus algorithm means that nodes send a lot of messages around, and eventually they will have consensus. And we intercept those messages, interpret them, and we forward them to the target chain. The good thing about those messages is that they're signed. You cannot fake them. And if the target chain receives those messages, and we build logic about the consensus algorithm also in the target chain, then the target chain can uniquely identify what the network actually decided for. This is very difficult to prove, but we actually prove that mathematically. And the mathematical proof is based on the correctness proof of the actual consensus protocol. And this is why the Stellar Oracle is mathematically provable as secure as the consensus protocol in Stellar. That means if you trust Stellar, if you trust your tokens in Stellar, you can also trust the tokens to the Stellar Oracle. And that's also why the bridge itself is as trustworthy as the Stellar Consensus Protocol. I would like to show a small demo about this part. Yeah?
What happens when the validators change? Do they change everything?
Yeah, they change. And this is also very complicated, but the validators can always change. First, you can become a new validator, or you can also leave the network of validators. And when you do this, and you can also change the nodes that you trust. But you always, with every message you send around the network, you always add the nodes that you trust. You put that into the information, and we can interpret the information. And as long as 2/3 of the nodes are not Byzantine and reliable, you can prove that you can trust the information. So what I have here are actually two components. One is a simple parachain that one is a simple substrate chain that implements this palette in a very simple way. It's not the complete one yet, as Spacewalk is not done. The Spacewalk Stellar system is not done, but I will say more about this. So I start the chain here. You probably know this. That's a typical output of a chain. And then I start the Stellar Oracle component that forwards the information on the other side. So it would just be some log output. What I want to do now is to actually send some money inside the Stellar network to one of the vaults. And in order to do this, I will use a Stellar wallet. It's actually a wallet that we built. It's called the Solar wallet. And yeah, I think I need to zoom in like this. Then you can also see this. So I want to send some tokens now to a vault account. And fortunately, I have the address of the vault account right here. So there we go. So we just send a small amount, like a tenth of a lumen. The lumen is the native currency, the native asset of a Stellar, in case you're not familiar with it. I also add a demo. That's also important. It's for the protocol itself. And here just for the demo. Now I send that lumen. And what you will see on the left-hand side is that this component, Stellar Oracle component, will now intercept the messages, and we'll see that they are there. And it now sees that a lot of the nodes in the Tier 1 validator network actually approved of that transaction. They have consensus on this now. Consensus is very quick in the Stellar Consensus Protocol. It finalizes immediately, and the consensus algorithm runs every 6 seconds. So we already have a finalized block here. And this information is now forwarded to the palette. And yeah, it's actually up here. Because there's a lot of noise in the substrate output, we put a warning here just so that it's more visible. It's actually not a warning, but you can actually see that now it successfully constructed some encoding here, and it actually could verify that the message arrived there on this side. Yeah, it also says that Stellar transaction is, there's a problem here, but that's just because of the demo and because it's a testnet, but it's actually working. And so let me continue. Okay. There's a question? You can also send back. If you send a transaction back, also the Stellar Oracle is important. I just quickly go back to how that actually looks like. So if you send a token back to the pallet will then burn the token, and then whenever you do this, you identify the vault that you want to interact with. You identify the vault that locks your tokens and should send it back. That vault will then observe that. The vaults, they need to be active. They need to actively observe what's actually happening, and will then unlock the token. The vault then needs to prove to the pallet that it really unlocked the token. Because if the vault does not unlock the token, and they just keep it for themselves, then it's obviously already a misbehavior. That's not what they are supposed to unlock the token. And they need to prove it to the pallet. if in a certain amount of time they don't provide a valid proof that they unlock the token and send to the target, then their collateral will be slashed because they're already considered to be misbehaving. Yeah, and it's a typical sign of misbehavior. So also in this case, you definitely need the Stellar Oracle to prove that. Just wanted to quickly point out that this was supported. I already said it was supported by a Web3 grant. This bridge, and we just finished the second milestone of that grant, which is about the Stellar Oracle. We are currently working on the third milestone, but Stellar is the Spacewalk Stellar instance is supposed to get ready next month, and we will launch it together with Pendulum in February. But as I said already, it's also open for any other parachain. And I think I'm actually already at the end, because I went into some more technical details. But yeah, hope that you enjoyed this. Thanks a lot.